How did engineers pack loose sand underwater to make it hard as steel without using a single drop of concrete? Right now, millions of tons of heavy luxury mansions sit on an island made entirely of sand and rock. One bad storm or underwater earthquake should turn this whole place back into a muddy ocean floor within minutes. So, why isn't Palm Jumeirah sinking? Let's dissect the impossible physics holding this island above the waves. Imagine wanting to build a giant toy city shaped like a palm tree right in the middle of the sea. That was the dream for Dubai. They wanted to make their coastline much longer so more people could live near the water. But there was a huge problem right at the start. Usually when people build big things in the ocean, they pour giant concrete legs deep into the seabed. For this island, however, the rules were strict. No concrete allowed for the ground itself. So, where do you get enough land to build an entire city? Dubai is covered in desert sand. So, you might think engineers could just scoop that up and throw it into the water. But desert sand is smooth and round from the wind like tiny glass marbles. If you throw marbles into water, they just slide around and refuse to stick together. If they used desert sand, the ocean would wash it away instantly. They had to go out into the deep ocean and dig up sharp, rough sand from the seafloor instead. Huge ships sailed out into the ocean, scooped up millions of tons of this rough sea sand, and sprayed it into the water like gigantic water guns. Slowly, a huge mountain of wet sand began to rise out of the sea. But this brought another terrifying problem. When sand is soaked with water, it acts like a liquid. Think of making a castle on the beach. If the sand is too wet, your castle just turns into a sloppy pile of mud and flattens out. If you try to build heavy roads, tall hotels, and big houses on top of wet, loose sand, the ground simply gives way. The weight of a building squeezes the water trapped between the sand grains, pushing the sand apart. The moment a heavy truck drives over it or a tiny shake happens in the ground, the whole island would sink like quicksand. The island was basically a giant water balloon ready to burst under its own weight. This left engineers stuck in a massive puzzle. They had billions of tons of loose sand sitting underwater, and they needed to turn it into a foundation as hard as rock without using any concrete. But before they could even figure out how to squeeze the sand together, they realized something even scarier. The big waves from the open ocean were already coming to smash their delicate sand pile. Before doing anything else, they had to build a giant shield. Before engineers could even touch the sand pile, they had to build a giant ring around it to act as a wall. This ring is called a breakwater, and its job is simple: to block the giant ocean waves from hitting the island. But how do you build a wall in the middle of the sea when you cannot use concrete? You have to use giant heavy rocks, and not just any rocks. These rocks were so big that each one weighed more than an elephant. Trucks drove back and forth to carry millions of tons of solid mountain rock to the coast. Ships then carried these giant rocks into the open sea and dropped them directly into the water right where the wave shield needed to be. They built the wall in layers: smaller stones at the bottom, medium rocks in the middle, and massive boulders on the outside facing the open ocean. When a giant wave travels across the ocean, it carries a crazy amount of energy. If that wave slams into a flat, solid wall, it behaves like a massive hammer blow, eventually breaking the wall down. So, engineers tilted the rock wall at a clever angle. When a wave hits this sloped wall, it forced the wave to roll upward, lose its speed, and spill harmlessly over the top, like water overflowing from a bathtub. Instead of trying to fight the ocean with brute force, the engineers designed the rock shield to trap and trick the water. The giant boulders on the outside of the wall were not glued together. They were stacked with tiny gaps between them. When a powerful wave crashes into the wall, the water rushes into these small gaps, loses its pressure, and gets trapped inside the spaces between the rocks. By the time the water comes out the other side, its force is completely gone. Even with this clever rock design, there was still a big risk of the ocean washing the sand away from under the rocks. If the sand under the wall got sucked back into the ocean, the heavy rocks would sink and the whole shield would collapse. To stop this, engineers laid down a special heavy fabric on the seabed before dropping any rocks. This magical fabric let water pass through, but kept every single grain of sand trapped beneath it. Finally, after dropping millions of tons of rock and creating an 11 km long ring, the giant shield was complete. The water inside the ring became as calm as a swimming pool, fully protecting the delicate sand mountain from the violent ocean waves. But now, another huge challenge was waiting for the team. How were they going to draw a perfect shape of a palm tree in the middle of the ocean without making a mistake? Now that the seawall was protecting the area, engineers faced a brand new puzzle. How do you draw a giant palm tree right on top of the open ocean? If you were drawing on paper, you can see the whole picture easily. But when you are standing on a ship in the middle of the ocean, all you see around you is blue water. You cannot put wooden sticks or measuring tape into deep water to mark where the sand should go. If a dredger ship sprayed sand just a few meters off target, the famous fronds of the palm tree would look lumpy, crooked, or completely ruined. To make matters harder, sand moves underwater, so they could not just guess where to throw it. The shape had to be so precise that every single leaf of the palm tree needed to curve at the exact right angle. They needed a giant ruler in the sky to guide them. So engineers looked up into space and turned to satellites. High above the Earth, private satellites were locking their eyes onto the exact coordinates of Dubai's coastline. But standard GPS back then was not accurate enough for this job. It could be off by a few meters, which would be a total disaster for a shape as delicate as a palm tree. To solve this, they built a special radio tower on the land nearby. This tower talked directly to the satellites in space and corrected their signal every few seconds. By combining satellite signals with the land tower, engineers created a super accurate guiding system. Suddenly, they could pinpoint any spot in the ocean with an accuracy of just a few millimeters. They installed this high-tech guidance system directly inside the control rooms of the dredging ships. Inside the ship, a computer screen showed the exact drawing of the tree. As the ship moved across the water, the computer guided the captain like a video game, telling them precisely when to start spraying sand and when to stop. Pipe by pipe, ship by ship, the satellite-guided dredgers sprayed sand into the exact spots marked by the sky. From the water level, it still just looked like a messy sand pile rising out of the sea. But when the astronauts aboard the International Space Station looked down, a perfect giant palm tree was appearing in the blue Gulf. Yet, even with the perfect shape drawn, the most dangerous part was just beginning. The sand beneath the water was still completely soft and ready to collapse. Now, the palm tree shape was floating in the water, but it was basically a giant landmass made of loose, wet sand. If a builder tried to put a heavy hotel or a house on top of it, the sand grains would slip away from each other, and the whole building would instantly sink into the ground. Remember, they could not use concrete legs down to the ocean floor to hold the buildings up. They had to somehow turn this soft sand into a solid rock floor. To understand how soft sand becomes hard, think of a bucket full of dry cereal. When you first pour the cereal in, there are lots of empty air pockets between the pieces, making it take up a lot of space. But if you shake the bucket gently back and forth, the pieces settle down into those empty gaps, fitting tightly together. Engineers needed to shake the entire island to settle the sand grains. But how do you shake a whole ocean island? They brought in specialized construction rigs equipped with giant, heavy metal probes called vibroflots. Imagine a metal pole as long as a 5-story building that vibrates at an insanely high speed, like a colossal electric toothbrush. Crane ships and trucks lowered these massive shaking poles straight into the wet sand, pushing them all the way down to the solid ocean floor. As the giant pole vibrated deep underwater, it sent powerful force waves through the sand. It also shot high-pressure jets of water out of its tip to help it slide deeper. This intense shaking forced the water trapped between the sand grains to shoot out to the surface. Without water holding them apart, the sharp sand grains collapsed in on each other, locking together tightly like microscopic puzzle pieces. As the sand packed down tightly, the ground level actually dropped because all the empty space was gone. The workers then filled the newly formed craters with more sand and vibrated the spot again. They repeated this process over and over, poking tens of thousands of deep holes across every single frond of the palm tree. Day and night, the island was shaken until there were no air or water pockets left inside the ground. After months of continuous vibrating, a miracle happened. The soft, muddy sea sand became so dense and tightly packed that it transformed into a solid layer as hard as concrete. Engineers drove massive, heavy trucks over the newly shaken ground, and the land did not move even a millimeter. The island was finally solid enough to hold a city. But a new, invisible danger was waiting just around the corner: stagnant ocean water. Now the island was rock solid and fully protected by the giant stone breakwater. But solving one problem immediately created a new, gross problem that nobody saw coming. Because the rock wall completely encircled the palm tree, the seawater inside the fronds became completely trapped. There were no natural waves or currents inside the bay to push the water around. Imagine filling a swimming pool with salt water, leaving it under the burning hot sun, and never turning on the water filter. Within just a few weeks, the trapped water becomes warm, loses its oxygen, and turns into a smelly green swamp. Algae grows everywhere, fish die, and the water starts to stink. Nobody would ever want to buy a multi-million-dollar luxury mansion next to a smelly, dirty lagoon. Engineers realized that making the water completely calm was a huge mistake. To keep the ocean clean and clear, the water needed to move continuously. Normally, the ocean uses natural tides to flush itself clean, with water rising and falling twice a day. But because the breakwater wall was a solid barrier, the natural ocean tides could not get inside to refresh the lagoon. So, how do you make a trapped ocean move without breaking your protective shield? The engineers decided to give the rock wall two giant slits, like opening two secret back doors in a fortress. They cut two wide gaps directly into the outer crescent of the breakwater ring. Now, the open ocean water had a way to get inside, but this brought a new danger. Wouldn't big storm waves just rush through those open gaps and destroy the island? To prevent big waves from causing damage, they built clever underwater bridges across those two gaps. When a high storm wave hits the gap, the underwater bridge forces the wave to break and lose its violent energy before reaching the inner bay. However, the normal, gentle movement of the daily tide can easily pass over the bridge and enter the palm tree fronds. This simple but genius design turned the ocean into its own natural water pump. Every 12 hours, as the tide rises, fresh, cool water from the Persian Gulf flows in through the gaps. As the tide goes out, it pushes the old water back into the open sea. Thanks to these two small gaps, the entire water around the palm tree completely replaces itself every 13 days, keeping the water crystal clear forever. With the water clean, only one final terrifying threat remained: earthquakes. Even with the sand compacted and the water crystal clear, engineers had one final nightmare to face: earthquakes. The Persian Gulf sits close to active tectonic fault lines. While a strong earthquake can shake a normal concrete building on land, an earthquake striking an island made entirely of wet sand creates a terrifying phenomenon called soil liquefaction. To understand liquefaction, imagine taking a jar filled with wet sand and tapping it quickly on a table. The sand instantly turns into a watery soup, and any small object sitting on top sinks to the bottom. When an earthquake hits, the sudden shaking squeezes the tiny spaces between the sand grains, forcing water upward under extreme pressure. Within seconds, solid ground turns into a liquid trap. If an earthquake triggered liquefaction on Palm Jumeirah, the consequences would be catastrophic. The hard-packed sand foundation beneath the luxury hotels and villas would turn into liquid mud. High-rise towers would tilt and collapse, roads would split open, and the entire island could literally slide back into the ocean floor. Because engineers were strictly forbidden from using traditional concrete foundations for the main island landmass, they had to invent a clever way to protect the future buildings from this liquid trap. Before laying down any bricks, they used a technique called deep dynamic compaction. They dropped massive steel weights weighing up to 40 tons from giant cranes high in the air onto the ground over and over again. This intense pounding forced any remaining water and air pockets out of the sand, bonding the grains together so tightly that water could no longer force its way between them during a sarceny. Additionally, when it came time to build the heavy skyscrapers and mansions, architects placed flexible, shock-absorbing foundations directly on top of the ultra-compacted sand layer, allowing the structures to move safely with ground vibrations. Thanks to these extreme compaction techniques, the island was designed to survive major earthquakes without turning into liquid mud. The loose ocean sand had been transformed into a fortress capable of standing strong against waves, stagnant water, and tectonic shocks. But as time moves forward, an even bigger question looms. Can this man-made miracle survive the test of time and climate change? Palm Jumeirah stands today as one of the most audacious engineering triumphs in human history. Engineers successfully turned over 90 million cubic meters of loose sea sand and 7 million tons of rock into a thriving, world-famous city. They proved that with clever physics, satellite guidance, and intense vibration, humanity could build a stable paradise right on top of the ocean without using a single drop of concrete for the land. However, living on top of the sea means playing a continuous high-stakes game against nature. Even though the sand is compacted like steel and protected by a massive breakwater, the ocean never truly rests. Natural water currents and strong winds are constantly trying to erode the coastline, slowly nibbling away at the edges of the palm fronds and dragging sand back into the deep water. To prevent the island from shrinking, engineers must constantly monitor the shape of the beaches. Whenever the ocean washes away a section of sand, specialized maintenance ships are called in to dredge fresh sand from the seafloor and spray it back onto the shores. It is an endless battle of maintenance, keeping the artificial coastline intact year after year. As global climate change accelerates, a much bigger challenge is approaching the horizon: rising sea levels and more aggressive ocean storms. Because Palm Jumeirah sits just a few meters above the waterline, any significant rise in the ocean level could place immense pressure on the breakwater wall and threaten the low-lying mansions on the fronds. The future of Palm Jumeirah depends on humanity's ability to keep innovating and adapting to the changing planet. Engineers are already designing smarter coastal defenses, advanced pumping systems, and artificial coral reefs to absorb wave energy before it ever reaches the shore. The island is not just a luxury playground. It is a giant living laboratory for how future coastal cities might survive. The story of Palm Jumeirah proves that human ingenuity can accomplish what seems mathematically impossible, but it also serves as a humble reminder that no matter how advanced our technology becomes, we never truly conquer the ocean. We merely borrow space from it. As long as the tides keep moving, the fight to keep this magnificent sand castle above the waves will never truly end.